So in this video, we're going to see how reflection can be used to form an image of an object. So we start with a flat mirror, which is called a plane mirror. And so we put an object in front of this mirror, and it emits light rays in all directions, but some of them are going to hit the mirror and then bounce off by the law of reflection. So say we have an observer standing here, and some of the light rays that bounced off the mirror are going to reach this observer. So what does the observer see? Well, an image is going to form where the light rays either diverge from or appear to diverge from. So in this case, if we follow the straight lines of these rays reaching the observer and extend them behind the mirror, they all converge at this point over here. So the light rays appear to diverge from this point behind the mirror. So at this point, a virtual image is going to form. An image can be either virtual or real. And we say the image is virtual if the light rays only appear to diverge from that point. They never actually pass through the image. A real image is formed when the light rays actually pass through it. They actually do diverge from that point. So again, an image forms when light rays either diverge from or appear to diverge from a single point. And so for a plane mirror, the image formed by an object is always going to be virtual, behind the mirror, upright, which means it's facing the same direction as the object, and it's also going to be the same size as the object. And also in a plane mirror, if the object is placed a distance s in front of the mirror, then the virtual image will be that same distance s behind the mirror. So now we're going to look at curved mirrors, also called spherical mirrors, because they're just a section of a sphere. So the center of curvature of the mirror is the center of the sphere from which the mirror is cut, because remember, the mirror is just one side of the sphere. And then the horizontal line along the center of curvature through the middle of the mirror is called the principal axis, or sometimes the optic axis. So the first type of mirror we have is a concave mirror. Now these guys curve away from the incoming light. So in a concave mirror, all the incoming or incident light rays, which are parallel to this axis, they're all going to pass through the same point along the principal axis after they're reflected. So all these light rays are converging at this point, which is called the focal point. Now if you wanted to see why this happens, then you could analyze each ray individually using the law of reflection and of course the normal line. In a spherical mirror, the normal line at any point along this mirror is a radius of the sphere. So the normal line always points to the center of curvature. So incoming parallel rays always converge to the same point after reflection from a concave mirror. And if the incoming rays are not parallel to the principal axis, but they are still parallel to each other, then they converge to a point which is above or below the focal point. Now this line here is called the focal plane. But the most important case is when the incoming rays are parallel to the principal axis, they will then converge through this focal point. And so we call the distance from the focal point to the mirror surface the focal length, which we represent by this curly f. So in most cases with the concave mirror, if you put an object in front of it, a real image is going to form. So we're going to look at one example where the object is behind the center of curvature. So when determining where the object will form, or where the image will form and what kind of image will form, you're going to be drawing a ray diagram of the mirror. And so there are always a few rays that are very easy to draw, because the object emits light rays in all directions. But if we just pick a random ray, then it's going to be hard to analyze where it bounces after reflection. So for a concave mirror or any spherical mirror, there are 4 easy ways to draw. The first is if the incoming ray is parallel to the principal axis, then it's going to reflect through the focal point after it bounces off the mirror. We already talked about this case. Second, if an incoming ray passes through the focal point on its way to the mirror, then it's going to reflect off parallel to the principal axis. Third, if the incoming ray passes through the center of curvature, it's going to reflect back on the line from which it came. And this is because, of course, the normal line at any point on the mirror passes through the center of curvature, which means this ray that passes through the center of curvature on its way here is already along the normal line. So by the law of reflection, it's just going to reflect back on the normal line. And the fourth ray that's easy to draw is a ray that goes from the object and hits the mirror at its center, which is also called the vertex. Now, a ray that hits at the center is going to be reflected at the same angle from which it hit the mirror. Of course, this is just the law of reflection, so you can see the normal line at this point, the vertex, is just the principal axis. So whatever angle that the light ray makes with the normal when it hits the vertex is the same angle as it's reflected at. So whenever you have a ray diagram, you're going to try to draw those 4 rays first. Now, sometimes you can't draw all 4 of these. For example, if your object is here in front of the focal point, then obviously you can't draw this ray which passes through the focal point. So you just have to draw as many easy rays as you can, and then see where these rays converge at or appear to diverge from. So we draw these 3 rays here, and they all converge at this point. So an image is going to form where the rays converge. And so you can see we draw a line from the principal axis to this convergence point, and it turns out that the image is upside down from the original object. We call this an inverted image. So this is also a real image, since the light rays actually do pass through this point. They actually diverge from this point. They don't just appear to diverge from this point. So all real images have to be inverted. And oppositely, all virtual images are going to be upright. Okay, so the other type of spherical mirror is a convex mirror, which curves towards the incoming light. And so all incoming rays parallel to the principal axis are going to diverge from a virtual focal point, or just the focal point, but this time the focal point is behind the mirror. So these incoming rays don't actually diverge from the focal point, they only appear to diverge from the focal point. As you can see, if we extended this reflected rays line back behind the mirror, it passes through the focal point. So a convex mirror will usually form a virtual image, or it will form a virtual image. So the rules, the easy ways for a ray diagram in a convex mirror is the same as a concave mirror, just with a couple of modifications. So remember, the first ray, parallel to the principal axis, it reflects through the focal point. Well, in a convex mirror, same thing, but it appears to diverge from the focal point. It doesn't actually pass through it. The second, if the ray passes through the focal point it will reflect parallel to the principal axis. In a convex mirror, obviously the ray can't actually pass through the focal point, but if it's going towards the focal point, so the light is incoming, and if it was to keep going, it would pass through the focal point. But obviously it stops here, and then it's going to be reflected parallel to the principal axis. And then the third ray passes through the center of curvature, it reflects back on itself. Well, it's the same thing. If it looks like it's going to the center of curvature, then it's going to reflect back on itself. And the fourth ray is the same. If it hits the mirror at the vertex, at its center, it's going to be reflected back at the same angle that it hits, due to the law of reflection. So again, a convex mirror is always going to form a virtual image, because the rays are only going to appear to diverge from that point. They're not actually going to pass through there.